Okay, let's go over the coding problem that I did today. I had to learn a new kind of data structure, kind of approach to doing this. So it's kind of this code was kind of I tried to write it out myself, then I used AI to comment it. So this is what we have. And let's go over the problem. It's just a variation of what we did yesterday. But the only thing that kind of changes is keeping the count. So yeah, we have the ranges as usual, given in range, your task is to count for each range how many other ranges it contains and how many other ranges contain it. Range of A, B contains range C, D if A is smaller than or equal to C and D is smaller than or equal to B. Okay, so we just have the integer input and then the output. Output is just basically first, before it was just the flag, Boolean flags. Now it's just counting how many there are, right? So now we're keeping count. So the problem with if we were just to copy the code from before and just write the whole thing would be that like we can't just keep count like keeping count and updating that would be problematic since our data is quite large. And then we would kind of just run out of space and also have time limit errors because it's just not a good data structure to deal with. So instead, what kind of our approach here would be to use a data structure kind of called bits tree, or also known as a person called F, Fenwick tree. So like it's there's two names for it. So the idea behind this tree is that it kind of optimizes two things, both like searching things up and also updating things. So then it can do both at login rather than if we were to have a prefix sum, let's say. Um, it would be very fast at lookup, but the problem for that is that updating it, for instance, if it was the first element we need to update it, everything after that has to be updated, which would be terrible. And it's the same with like let's say um a sorted array that kind of you can store and update things easily, but your lookup is very like large. So that's why this is kind of like the in-between sort of thing. Both are login, so it's relatively good. So how we did this was we still kept our struct called range, and then we still kept the same function compare, which basically we just compare and sort it so that we first sort it based on ascending left, like the ascending left value. And that if that is equal, then we kind of sort the right by descending order. So it's the same logic that I explained yesterday. And then this is kind of the new part that we added is our struct, which we called Fenwick tree. Inside here, we kind of first define the maximum size as n. Next, we have a vector, which we call tree. And then we define our constructors. So we have our Fenwick tree of takes integer n, and then we have the n and then the tree. And that because Fenwick trees are one indexed, we need to create one more, so it's n plus one. And then we can start making like different kind of functions with it, right? The first one is add. If we need to add update some value to it, for instance, delta to an index I, then what we do is like our parameters are I and delta, and then we start at I, and then we keep adding to the lowest significant bit to kind of hop forwards and update everything in the list, right? So if you don't know what kind of like the Fenwick tree is. It's essentially like it kind of is like a binary index tree where like um it takes the idea of prefix sum but kind of breaks it down into like the chunks. Like the chunk sizes are like 1, 2, 4, 8, like powers of 2. And what it does is that like in each part, it's the size of that would be the um least significant bit. For instance, let's say here that index 6 is 0, 1, 1, 0 in the thing. So then the least significant bit would be this 1 because it shows up first, and that's in the twos column. So then this index 6 would hold two items, which would be just 5 and 6. And then the math behind this is to access it is like I and negative I, so then we can kind of just get the least significant bit. And then it's kind of just like updating and changing it. So that's kind of like a prefix sum, but not exactly. You don't have to update the whole thing, you can hop around. So that's why we can get it to log in. And then what we do is inside the add function, we just need to update everything that has this least significant bit, right? It's like the larger chunks that contain that. So then it's just like for um when I is smaller than n, we just go to the next one, next least significant bit that contains it. So then we just update our tree I to be plus equals delta. So then we increment that by delta. Everything that contains that previously. And in our query function, what we do is we're interested in what it's at the sum from 1 to I, right? So then we just keep track of our sum, which we initialize as 0. Then we just have a for loop of going through all the things that contain it, right? So we're going to go from I greater than 0 all the way, every time we just move to the um, subtract off the least significant bit because we're kind of going back. So like if something includes that, we just kind of subtract it off. So then we would just collect every piece of the sum. It's like if like let's say our thing was like 1 0 1 0 1 1, then we would just kind of collect each piece of the 1 1 1 1 slowly, like just collecting each of the one pieces. That would just be the idea behind this for Curie. And then here we would just have the for loop, and then we just make sure that sum is added to that, and then we would return our sum. And then now, since we implemented both the add and the query for the tree, what we can do is in our main, we can start actually using it. So in the first part, we have to make our input and output faster. We have iOS-based Sync with Studio in scene.ty. Next, we have our int in, and then we would input the in. And then we create our own vector, which is range, and also y chords, which is basically just to hold the right values. And then what we do is inside here, we would input what the ranges are and then store the like the indexes, and then in the y chords, we also push the right endpoints. And then we actually start our kind of like actual processing of the data. So what we're going to do is we're going to first sort it on the right index. So then this kind of just does the sort. Next, what we do is we don't want any duplicates. So because the array could be very, very large, so 1 all the way to 10 to the 9, like we want to store it in a array, but we can't create a array that large, right? So more realistically, what we're going to have to do is we just store it based on the rank and then convert the rank. Like basically, for instance, if it was very large, then it would just be like a number, like ranking it in terms of other 1, 2, 3, 4, 5, 6, rather than like a very large value and a very small value. So we take advantage of the space. And then that's why we can later, since we store it, then we can recover it. And that's how we do it. And the next one we have is y chords dot erase unique of this. So then we make sure that there's kind of no like duplicates to remove that issue. And then we would just get the highest rank for our tree, pretty straightforward. And then we would sort the ranges based on the comparison function. So that is basically the same as yesterday. And then creating the vector, this is the same as yesterday as well. The contains and the contained by. And then we have our tree, which we call bit contains, and then we kind of just create a tree of the maximum. So we make sure that we don't see. That's where why we have the maximum rank, so we take advantage of knowing that size. And then we kind of just work. This is the same logic as before from yesterday. We kind of just work backwards from right to left, and then our for loop kind of just checks the boundaries, and it's the same, and checking if it contains this. And then we work backwards from left to right now, and then we check. It's the same thing from yesterday, but now it's just in terms of using the tree that we just did. And once we finish processing, we would just output the thing of the contains and the contained by. I'd say this question was definitely difficult because I didn't know about this kind of thing before, but I think I got to learn about it and I think it's pretty cool. Let's end off here.